Hello, welcome back to the first course in General Physics. We are now in the sixth part of discussing the subject of thermodynamics of systems, and we are in the region of discussing the entropy and the second law of thermodynamics. So in this lecture, we'll be concerned with the arrival at the second law of thermodynamics from the basic principles that we have discussed in the previous lectures. And then after that, we will come to the discussion of heat engines, and we will construct the ideal and perfect engine. And in this regard, we will be focusing our attention on an ideal engine, which is the Carnot engine. So in the beginning, we will start where we ended our discussion last lecture. In the last lecture, we have arrived at a conclusion that we should modify the postulate of entropy in order to be applicable to processes which are reversible, as well as to processes which are irreversible in a closed system. And we concluded that in reversible processes, the entropy of the system, of a closed system, remains constant, while in irreversible processes, the entropy of a closed system increases, and the entropy in any case will never decrease. This postulate leads to the construction of a mathematical form of the statement, which is called the second law of thermodynamics. And this second law of thermodynamics states that in a closed system, the entropy change of the system, delta S, is equal to or greater than 0. This is a mathematical statement of the lately modified postulate of entropy. Thus, delta S is greater than 0, which is part of the second law of thermodynamics. This applies to irreversible processes. However, the equal sign in the second law of thermodynamics, delta S equals 0, applies to the reversible processes. This is the important second law of thermodynamics, which has various applications in real life and in the real world, as we will be discussing soon. Now we come to the discussion of heat engines, or thermal engines, as some people call them. What is a heat engine? A heat engine is a machine, is a device that operates between two temperatures and exchanges heat with the environment. And in the process, it does useful work. Thus, in the operation of an engine, there is a heat exchange involved and doing or performing useful work. And that is why we construct such machines, in order to be able to obtain work done by these machines, such as driving a car or lifting objects or doing some other type of any useful work. A heat engine is a machine or a device that operates between two temperature reservoirs, one at a higher temperature T sub H, and the other one at a lower temperature T sub C. And operating between the two reservoirs, it extracts energy or heat energy from the high temperature reservoir, and it does work and it exhausts some heat into the lower temperature reservoir. And depending on what are the high temperature reservoir and the low temperature reservoir, that would be characterizing the machine and the operation procedure of this engine. Heat engines contain inside them working substance, a substance that exchanges the heat with the reservoirs. It is the medium for the interaction between the machine and the heat reservoirs. And the working substance is the substance that performs the work, that delivers the work to the environment. So this is right at the heart of each heat engine. Like a gas, for example, or in some machines. And the working substance in the heat engine works in cycles. Each cycle, each closed cycle, consists of a series of processes of special type that is characteristic of the engine itself. These processes, each one is called a stroke. So we have, each cycle consists of a series of strokes which start from an initial state of the substance and comes back to the initial state, to the same initial state of the substance. This is a complete cycle, and during the complete cycle, the machine or the engine absorbs heat or extracts heat from the high temperature reservoir, does work, which is the work involved in the loop of the cycle, and it exhausts in the process some waste energy due to the lower temperature reservoir. Now, if we want to start discussing the engines, we would like to construct a picture of an engine, first of all. And in that regard, we consider an ideal engine. An ideal engine is a special type of engine that does not include wasting energy in the process of operation. A Carnot engine is such a hypothetical engine, which is an ideal engine, and this engine is proposed by Carnot back in 1824, and this is the construction of the engine. It's a diagram that constructs the operation of the engine, and the diagram simply shows a system which consists of a working substance right at the center of the engine, and this cycle, sort of closed cycle with these arrows, indicate that the system goes through a cyclical process, and the engine extracts energy Q sub H from the high temperature reservoir, which is at T sub H. It extracts this energy. It does work, and this work, usually we can use it to perform some jobs, and in the meantime it exhausts an amount of energy Q sub C to the reservoir, which is at temperature T sub C. And as we mentioned, this is an ideal engine, and in an ideal engine we assume that all processes are reversible, in the sense that there are no dissipative forces. We don't have wasteful energy. We don't waste energy in the process. So we don't have forces like friction between the various parts of the engine. We don't have turbulence for the fluid that is involved in the operation of the machine. We don't have such effects, and that is why we call it an ideal engine, an engine that operates without losing energy via the irreversible processes. Let's look at the cycle that we just mentioned for the working substance in the Carnot engine. The cycle in a Carnot ideal engine, it's the same word, Carnot engine or an ideal engine, consists of 4 strokes. Each cycle consists of 4 strokes. The first stroke is an isothermal stroke, which is the stroke through the path AB. In this stroke or process, isothermal process, the system is taken from a state, an initial state, which is A, to a final state, which is B. In this process, the system absorbs heat Q sub H from the high temperature reservoir at T sub H. And then after that, the second stroke is the stroke BC. And this process, BC, is an adiabatic process through which no heat exchange occurs between the system and the environment. So from B to C, Q is equal to 0. It's an adiabatic process. And now this process from B to C takes the system from a higher temperature, T sub H, to the lower temperature T sub C without any loss of heat or absorption of heat. It expands adiabatically. And the third stroke is an isothermal process. It is an isothermal compression where the gas is compressed from the volume V at state C, V sub C we can call it, to the volume at the state D, which we can call V sub D. So this is an isothermal compression where, because it's isothermal, the work done is equal to the heat exchanged with the lower temperature reservoir, because the system now is at T sub C at the lower temperature reservoir, at the lower temperature of the cold reservoir. So as it compresses, the work done is negative, and thus the heat is negative. That means the system loses heat to the colder reservoir. And the fourth stroke, dA, is an adiabatic process, and this adiabatic process takes the system from the state at point D, where it is at temperature T sub C and volume V sub D and pressure P sub D, up to the initial point adiabatically. So it takes the system back to its initial point at point A, at the initial state at A, where it gets back its initial state parameters. So it goes back to the initial volume, V sub A, and at the initial temperature, which is T sub H, that it started at, and at the initial pressure. So this is a full cycle which is characteristic of the Carnot cycle: isothermal, adiabatic, isothermal, and adiabatic, back to the first initial state. During this cycle, the system absorbs heat, Q sub H, from the high temperature reservoir and loses heat, Q sub C, to the lower temperature reservoir during the adiabatic, during the isothermal compression. The total heat absorbed during this cycle is simply Q sub H minus Q sub C. And since the working substance starts from an initial state and goes back to the same state by the end of the cycle, then the internal energy change is zero during this cycle, which implies that the heat absorbed, the total heat exchanged by the system, would be equal to the work done by the system. And the work done during this cycle is simply the area inside this loop, inside this cycle, consisting of the four processes, the four strokes. So the area A, B, C, D, back to A, the area within this loop is the work done during this cycle or cyclical process consisting of four individual processes, and that work would equal to the total heat absorbed during the cycle, which is Q sub H minus Q sub C. This is an important result to remember. Work done during one cycle is equal to Q sub H minus Q sub C. This is the result of the net work done during the cycle, and we write Q sub H and Q sub C as absolute values in order to ensure that we are dealing with the magnitude only, because the sign of the lower temperature of the heat lost to the lower temperature reservoir is negative, to indicate that the system has lost energy to the lower temperature reservoir. So the sign is included in the equation, and thus in absolute form we deal only with the magnitude. So Q sub L absolute value, Q sub C absolute value is actually a positive value, and Q sub H absolute value is also a positive value. This work, as we noticed from the area of the loop, is positive, which includes that the value Q sub H is greater than Q sub C. Now, in a full cycle, since the system starts from a particular state and ends with the same state, goes back to the same state, and since the entropy is a state functional or a state parameter that depends on the state itself, that means during a cycle the entropy change is zero. So the net entropy change delta S per cycle is equal to zero for the operating substance. And if we take into consideration a closed system, the working substance does not constitute a closed system. So consideration of the entropy change in the working substance alone will not be sufficient to take into consideration all the thermodynamic changes that would occur in a closed thermodynamic system. What is our closed thermodynamic system? We notice that the working substance exchanges heat with the higher temperature reservoir, QH, and it exchanges heat also with the lower temperature reservoir, Q sub C. And thus, if we include the higher temperature reservoir and the lower temperature reservoir with the working gas, we consider all of these as elements of one closed system, then we speak of the entropy change of the whole closed system. Since the engine by definition is an ideal engine, which means that all the processes are reversible, and in this case delta S total for all the system, if all the processes are reversible, should be zero. Delta S is equal to zero according to the second law of thermodynamics for a system, a closed system that has only reversible processes. Thus, delta S would be delta S for the working substance, for the gas, plus delta S for the high temperature reservoir, plus delta S for the low temperature reservoir. Since the gas starts from an initial state and goes back to its initial state again, delta S for the gas is zero. So that quantity is zero. So we are left with delta S for the whole system, which is 0, is equal to delta S for the high temperature reservoir, delta SH, plus delta S for the low temperature reservoir, which is delta S sub C. So we have this relation, 0 equals delta S sub H plus delta S sub Z, that is taken from the fact that we have an ideal engine, all processes are reversible. And in this case, we substitute for the values of delta S sub H and delta S sub C. Remember that delta S sub H is equal to Q sub H over T sub H, and Q sub C and delta C sub C, delta S sub C, I'm sorry, delta S sub C, the entropy change of the lower temperature reservoir, is equal to minus absolute value of Q sub C over T sub C, because, let me state it again. The total entropy change of the system is delta S sub H plus delta S sub C, and since the higher temperature reservoir loses heat to the system, then the heat absorbed by the high temperature reservoir is simply minus Q sub H. Thus, delta S sub H is equal to minus Q sub H over T sub H, and the lower temperature reservoir receives or absorbs energy Q sub C, which is a positive energy in this case, and thus delta S sub C is equal to plus Q sub C over T sub C. And thus we arrive at the relation 0 is equal minus Q sub H divided by T sub H plus Q sub C divided by T sub C, that's equal to 0. And then we just move minus Q sub H over T sub H to the other side of the equation, and we arrive at the important relation Q sub H, absolute value, that's a positive quantity, divided by T sub H, that is the heat absorbed by or released by the high temperature reservoir divided by its own temperature, is equal to the heat absorbed by the lower temperature reservoir divided by its own temperature of the lower temperature reservoir. That is an essential equation for the ideal engine, that applies to an ideal engine. This equation gives us the means to determine the ratio between Q sub H and Q sub C, which is simply T sub H over T sub C. And we conclude also from this result, since the temperature of the higher temperature reservoir is greater than the temperature of the lower temperature reservoir, looking at these two ratios, we notice or we conclude that Q sub H must be higher or greater in magnitude than Q sub C, which means that the system absorbs more heat from the higher temperature reservoir than what it releases to the lower temperature reservoir. And thus, Q sub H minus Q sub C is a positive quantity, and thus the work that the engine could do is a positive quantity. That is what we want, and that's why we construct such machines for. Now, we plot a diagram that shows the relation between the temperature and the entropy of the system. So we look at these 4 strokes on a TS scale. The stroke AB, or the process AB, is an isothermal process where it is at a constant temperature. So it's like a horizontal line. This is a constant temperature line. And during this process, the system moves from A to B. The entropy of the working substance increases as shown on the figure, and then the working substance goes from a state B at temperature T sub h, it goes down to a state C at temperature T sub C, and this process is an adiabatic process during which Q is equal to 0, and thus delta S is equal to 0 because it's an adiabatic process. So it's a straight line down, indicating that the entropy of the system is fixed during this process. And then we have an isothermal compression. We have an isothermal compression where the system, the working substance, changes the state from C to D at the same temperature, T sub C. And in the meantime, it loses energy to the lower temperature reservoir. It loses heat Q sub C, and thus the entropy of the working substance decreases by ds, by delta S in this process. And finally, the system goes from state D back to state A through an adiabatic process, and this adiabatic process is characterized by Q equals 0, and thus delta S is equal to 0. So this is the diagram of that illustrates the Carnot cycle, the 4 strokes on a TS scale. Now, if we are concerned about a factor that is of importance in the construction of engines, scientists and engineers, when they construct engines, they always dream of constructing perfect engines, engines that have as high efficiency as possible. A perfect engine would have an efficiency of 1. What is efficiency? Efficiency could be defined as what we want, what we need in terms of benefit from the machine, divided by what we pay for. So if we define the efficiency of the engine in such a manner, we arrive at this formula, which tells us that the efficiency of any engine in general is the work done by the engine divided by Q sub h. Why is that? That is because from an engine we want to obtain work done, useful work. And in the meantime, we have to supply the engine by an amount of energy. That amount of energy, QH, that we supply the engine with during each cycle of its operation is energy that we pay for, like fuel that we buy, and we burn the fuel in order to make the engine operate, as in the case of heating houses, for example, or as in the case of an automobile moving. So if we define this efficiency in this manner, then we use the formula that we have arrived at previously from our previous discussion, that the work done during any cycle in a Carnot engine is simply Q sub H minus Q sub C. Substitute this amount for the work done, and we will get the efficiency as 1 minus Q sub C over Q sub H. This is in an ideal Carnot engine. But we have a better means of measuring temperatures than measuring the amount of heat that is absorbed or released, because measuring a temperature would involve only a thermometer. So in that sense, we use the relation that is also applicable to an ideal engine that contains only reversible processes, in which case we have Q sub H over Q sub C is equal to T sub H over T sub C. We substitute this ratio or this value in this equation, and we arrive at the relation: the efficiency of a Carnot engine, which is an ideal engine, epsilon is equal to 1 minus T sub C over T sub H. This is the efficiency of an ideal engine. Of course, T sub C is smaller than T sub H, which means the efficiency of the ideal engine is somehow a quantity that is smaller than 1. In ideal engines, we could have, for example, an efficiency of 50 or 55% for an automobile ideal engine, or we can have a 40% efficiency for a nuclear plant, for example, that would provide us with electrical energy. But that is for an ideal engine. A 50% efficiency would be great. But in fact, in real world, the real efficiency of these engines will not exceed 25 or 30% in general, because we always have some dissipative forces. We have some energy lost that we do not encounter in the treatment of an ideal engine. The dream is to increase the efficiency. This is the job of the talented engineers and scientists, is to arrive at an engine that has as high of efficiency as possible. The real dream, the ultimate dream, is a perfect engine, and the perfect engine would have an efficiency of 1, epsilon equals 1, but engine, such an engine, means that it does not have at all any heat that is wasted, thrown away to the environment, to the lower temperature reservoir. And that engine would simply extract heat from the reservoir that is in contact with, from a reservoir at TH. It would extract such an amount of heat, Q sub H, and converts it completely into useful work without any loss of any heat in the meantime. That means Q sub C is equal to 0. That is true for a perfect engine. But what are the conditions for such a perfect engine? The conditions for such a perfect engine is that, if we recall the equation that gives us the efficiency. Efficiency is equal to 1 minus T sub C over T sub H. That means T sub C should be 0. If we put T sub C in this formula 0, then we'll get epsilon is equal to 1. That means the lower temperature reservoir should be at absolute 0. That's not 0 centigrade, that's absolute 0, which does not exist until now. By all the technologies that we have never reached absolute 0 degree Kelvin. So T sub C is equal to 0 is impossible. We have not arrived at such a temperature at all. And the other condition, alternative condition, is if we set T sub H is equal to infinity, because in this case T sub C over T sub H would be 0. This ratio would be 0 regardless of the value of the colder temperature reservoir. And that is also impossible because we cannot provide the system with an infinite temperature, because it simply does not exist, or it will melt everything. So that is also an impossible. So these conditions are impossible to obtain, and this leads to an alternative statement for the second law of thermodynamics. According to this experience of ours, that the second law of thermodynamics could be stated, depending on these facts, as follows. No series of processes is possible in nature whose sole result is the transfer of heat from a thermal reservoir and the complete conversion of this heat energy to useful work. It is impossible to obtain such a condition. That is the statement regarding the second law of thermodynamics. And as an example of machines, of engines, thermal engines, we have the Stirling engine. And the Stirling engine is an engine that's constructed by Robert Stirling in 1816. It's constructed as a real engine. And in this engine is similar to the ideal Carnot engine, but with minor differences, that the isothermal processes are the same as in Carnot engine. However, the adiabatic processes in the Carnot ideal engine are replaced in the Stirling engine by constant volume processes. So this would be the cycle of the Stirling engine, and this cycle shows that the system is taken from state A to state B isothermally, then a constant volume process, then an isothermal compression to D, and then a constant volume process back to A. Q sub H and Q sub C are the same as before. The difference is that in the constant volume processes, there is also heat involved, heat absorbed and released to the environment. But the heat absorbed in BC, in process BC, is equal and negative to the heat absorbed in dA. So what the system absorbs in BC is the same as it would release in dA. So the total net heat absorbed in the process is still Q sub H over Q sub C. And this is a Stirling engine. The ideal Stirling engine has a lower efficiency than a Carnot engine. And real-world Stirling engines have even lower efficiency. At this point, I would like to finish this lecture and thank you for your attention.